It was the spring of 1965, on the eve of the first manned missions in the long-developed Project Gemini, that a supervisor at JPL, Joe Cutting, head of the Advanced Projects Group, approached his team to conduct an in-depth study of potentially useful outer planet mission profiles and launch opportunities in the near future. With the conclusion of the International Geophysical Year almost a decade earlier, the United States had gone head-to-head with the Soviet Union in a robotic race to the moon, and had roundly lost. The allure of the moon and dominance in space proved irresistible, and had become the target of the much more popular, much better funded, and much more politically relevant manned program. Unmanned exploration through the 1960s progressed in a subservient role. Ranger and Lunar Orbiter were merely scouting trips, reconnaissance for later Apollo. The possibility, however, of flights to other planets had captivated and held the interest of many, in a way like nothing else except the Apollo missions themselves. That goal became the next logical evolution of the unmanned exploration programs. In retrospect, there tends to be an inflation of the perceived scientific focus of the unmanned programs, viewed in contrast to the political and technological superiority goals of the manned flights. This argument has often been made to downplay the scientific achievements of manned missions in favor of those of robotic missions, which are described as being more scientifically pure in design and intent. But for all the genuine importance of magnetospheric physics and gravimetric studies, it was quite simply the promise of photographs of the planets that appealed to a broad swath of the American public and lit the fire that would push unmanned exploration forward through the golden age of spaceflight. It was in this context that the United States and the Soviet Union opened a new chapter in their competition above the atmosphere, a race to the planets. This was also the first race in which the Soviet Union had experienced a loss, with the American mission of Mariner 2 reaching Venus in December of 1962. By 1965, when Gary Flandreau and his colleagues, part of Joe Cutting's team, were given the task of studying near-future opportunities for missions to the outer planets, it seemed intuitive. It was the next obvious step in a space race with snowballing momentum. Each and every year, budgets and ambitions climbed. It was unlikely, however, in 1965, that sufficient rocket power would be allocated to the unmanned program to facilitate outer planet exploration, which was, to put it a certain way, a whole new ballgame. Consider an imaginary solar system. Several planets orbiting around a centrally located star. The closer planets, more powerfully affected by the star's gravity, orbit faster. More distant planets not only have a much greater circumference to travel in their orbit, but because of gravity, or in this case the lack thereof, they also orbit more slowly. For interplanetary travel, minimizing fuel consumption is the name of the game. Gravity and velocity are the dominant factors in trajectory planning. If you're trying to get from the innermost planet to the outermost planet, you wait, allowing the planets to orbit the sun until they reach a certain magical position relative to each other. Launch at this moment, called a Hohmann window, and you can speed up, boosting away from your home planet and coasting outward, aiming for a point in space ahead of your target, and hopefully, with enough precision and a little luck, getting close enough to fall into its gravity well. Transfer windows between the Earth and any of the other planets in our solar system happen essentially all the time, at least once a relative year. They aren't incredibly special. But Flandreau's supervisor, Joe Cutting, was studying the application of an intermediate planetary gravity assist in mission profiles to Mercury via Venus. Think of it as a double transfer window. First, you take advantage of a window from Earth to Venus, and by the time you reach Venus, another transfer window will have opened between Venus and Mercury, allowing you to use Venus's gravity to bend your trajectory in just the right direction to send you there. No major engine burn is required, since you're already coming in at escape velocity, with too much energy for Venus's gravity to capture you on its own. This work would lead to the highly successful Mariner 10 mission in 1973. The idea behind a gravity assist was fairly straightforward: to minimize the amount of rocket needed to push an exploration payload, such as a robotic probe. If the gravity of a halfway planet could be utilized in some respect to bend that payload's outbound trajectory towards the final target planet, it would save precious weight and fuel. In 1965, such a strategy would be crucial for success, given NASA's limited lifting capability. This trajectory shaping method might just be applicable in outer planet exploration, and early on, Flandreau followed this road. Much of the theoretical work had already been done by people like German rocket engineer Kraft Ericke, and by astronomers and mathematicians of the Copernican age, such as Urbain Le Verrier, who knew about the importance of planetary gravity fields in perturbing the orbital paths of comets. Graphing of the heliocentric positions of the planets and analyzing their historical trends allowed Flandreau to make accurate predictions of planetary positions in the future. His work led him to realize that there would be a quadruple convergence just before the 1980s, a once in every 176-year occurrence where all four gas giants would be on the same side of the Sun and in the proper relative position for multiple outbound gravity assists. One probe, launched towards Jupiter sometime in the mid-1970s, with the utmost accuracy and precision the likes of which had never been attempted before and would not be necessary again, could, in theory, swing from Jupiter to Saturn to Uranus to Neptune, all without a major requirement of fuel after the initial boost out of Earth orbit. The genesis of this realization was spawned on the third floor of Building 180 at JPL in the summer of 1965. In an incredible coincidence, the convergence wouldn't happen for just over a decade, leaving enough time to design, market, hopefully fund, and build a spacecraft. Assuming, of course, the mission concept was approved. The four-planet mission profile came to be called the Grand Tour, and it began generating buzz when in 1966, Flandreau publicly published his findings. He outlined several possible profiles. There were two major constraints. The first, of course, was delta V, the necessary speed to attain this complex trajectory. This would be incumbent on both the weight and complexity of the probe itself, as well as the relative power of its launch vehicle.
The key here is to use free energy that you can, it's not using rockets now, we're using some free energy, which I will explain. Jupiter is moving along and it's pulling us with its gravity field. We sometimes call that gravity assist. Adds a tremendous boost of energy. That's equivalent to about 4 Saturn V rockets waiting for you out there. If you could hook those up, you can really get a tremendous boost in speed. Heads over there to Saturn, and you get a huge boost, and you can get then to Uranus really quickly, and then on to Neptune. And then we're on the way out of the solar system. That's where we go interstellar at that point. But the interesting thing here, and by the way, here I am doing these things. I say, how could we ever sell this? But the key to selling it is to notice that some important event happens within 4-year time spans.
The other constraint was time. This would be a mission like no other, one that would last not just years, but well over a decade, or possibly more. Gary Flandreau, still a student, would leave JPL long before his vision would be implemented. Dr. James Van Allen, the same Van Allen whose instruments on America's first satellite, Explorer 1, had discovered the radiation belts around Earth that bear his name, became a vocal advocate for outer solar system exploration during a period of shifting priorities and budget cuts for NASA. As support for Apollo waned, the promise of bigger and better unmanned missions filling the exploration role at a fraction of the cost now seemed highly appealing to the Nixon administration, which wanted to distance itself and establish a new direction away from the Kennedy and Johnson vision of American spaceflight. The scope of the Grand Tour project wildly fluctuated during this time. At one point, JPL considered 4 separate but identical missions to capitalize on the incredibly rare opportunity. But over at NASA, these proposals soon found themselves competing with the newly inaugurated Space Shuttle project for funding. NASA was slow to embrace Grand Tour. It already had its own outer planet exploration missions developed by a completely separate team.
Pioneer, reaching out to other planets once thought to be inaccessible, now within reach. It flies to Jupiter, takes pictures, then soars off through and beyond the solar system, beyond our comprehension of space and time.
Pioneer 10 and Pioneer 11, both of which would fly by Jupiter. Utilizing the gravity assist concept, Pioneer 11 would go on to fly by Saturn. Apart from a single onboard scientific instrument, JPL was out of the loop. The novelty of the Grand Tour concept had worn off, its very goals undercut by a different American robotic exploration team. In 1971, the 4-mission, 4-planet concept was officially rejected. In 1972, NASA instead approved something else entirely, called Mariner Jupiter-Saturn. It was to be a series of 2 identical flights, both of which would fly past the 5th and 6th planets. Little more than a rehash of Pioneer 10 and 11. But in NASA's thinking, the Pioneer probes, both of which will encounter Jupiter and one of which will continue on to Saturn, are small and fairly primitive. They are merely reconnaissance missions, leaving much to be desired as far as in-depth study is concerned. That is the official stated purpose of Mariner Jupiter-Saturn. JPL's probes would be more than 3 times heavier and much more sophisticated. NASA wants to use these probes to revisit these 2 planets and study them with a much more complex suite of instrumentation. The real kicker is that these probes would launch in the late 1970s, during the 4-planet alignment. Yet NASA had no plan to take advantage of it.
Everything we now do, every advance in knowledge we now make, contributes to that. And just because I can't see it doesn't mean it isn't there. And if we refuse to take those steps because we don't see what the future holds, all we're making certain of is that the future won't exist and that we will stagnate forever. And this is a dreadful thought. And I am very tired when people ask me what's the good of it, because the proper answer is, you may never know, but your grandchildren will.
Despite the limited official aims of these new flights, which were to utilize Gary Flandreau's late 70s launch windows, a culture of stubborn persistence developed at JPL. Despite a limited budget, engineers had every intention of designing spacecraft that would remain functioning well after the Saturn encounter, even if NASA had no public intention of operating beyond Saturnian space. There was a hidden, unstated agreement between the engineers and the scientists during the design and building phase of these flights. Those on the ground at JPL quietly acknowledged the possibility of pursuing a further encounter with Uranus, and possibly after that, even Neptune, should the spacecraft remain healthy.
By 1972, they had been sort of downsized to MJS-77, which is Mariner, Jupiter, Saturn, 4-year mission just to those 2 giant planets and their moons and rings. That, fortunately, was to be launched in 1977, however, so that if they continued to work, they could go on to Uranus and then finally Neptune, completing the grand tour of the outer planets in 12 years rather than 30 years.
Although it had been officially rejected, Grand Tour was slowly coming back from the dead, not by any top-down managerial decisions, but instead by an organic, bottom-up, quasi-conspiracy between those who truly believed in the importance of such a flight. Slowly but surely, over the years, secondary objectives were quietly tacked on, piece by piece. Regardless of which objectives or instruments the scientific community recommended for Mariner, Jupiter, Saturn, JPL insists early on including television cameras. Photography was to be a central aspect of these flights, and indeed, a slightly longer trajectory was chosen for the explicit purpose of providing the ideal lighting conditions for photography during the Jupiter and Saturn encounters. The design and experience from prior Mariner missions used wherever possible and supplanted with subsystems designed for the Viking orbiters. They requested the Atomic Energy Commission upgrade the plutonium RTGs so that they would last more than 10 years. They developed a reprogrammable onboard computer, something that would be critical to the prospect of an open-ended, long-term mission in space. Pioneer 10 traverses the asteroid belt in late 1972 and arrives at Jupiter in November of 1973. It passes Jupiter at a distance of 132,000 kilometers, some 71,000 nautical miles, and becomes the first man-made object to encounter the gas giant, and beams back the first ever photos of Jupiter in detail. The levels of radiation at Jupiter were much stronger than expected, by a factor of nearly 1,000, the product of a massive magnetic field. Pioneer 11 would itself encounter Jupiter a year later, and then begin a long, lonely journey towards Saturn, which it wouldn't encounter until 1979, well after the launch of the 2 JPL probes. The Pioneer encounter at Jupiter had a profound effect on the development phase of Mariner, Jupiter, Saturn. Because of the intense radiation encountered, far stronger than anyone had expected, certain scientific experiments initially selected were dropped, and others were added. Ultimately, there would be 11 chosen areas of investigation: imaging, radio science, IR and UV spectroscopy, magnetometry, charged particles, cosmic rays, photopolarimetry, which is to say the study of the intensity and polarization of reflected light, such as from clouds in a planet's atmosphere, planetary radio astronomy, plasma, and particulate matter. Each field of scientific inquiry has its own principal investigator, but the heads of the imaging and radio science groups were designated overall team leaders. The position of lead project scientist was given to Ed Stone, a magnetospheric physicist from Caltech who had been working on Grand Tour since 1970. Stone is keenly aware of the public's impact on space exploration, and vice versa, and firmly believes in the importance of communication and public relations. He decides early on that scientific findings will be crystallized, summarized, and shared with the public as soon as they are made available. The basic structure and beating heart of the spacecraft is called the bus. It is a large 10-sided box. On top of this box rests the high-gain antenna on what is called the Z-axis. The spacecraft is designed to roll about this axis via the firing of RCS thrusters attached to the bus. Each of the 10 sides contains a small bay that houses various electronic assemblies. Attached to the bus are several external components of varying purpose. The science boom anchors 3 instruments dedicated to studying particles in space: the cosmic ray instrument, the plasma science instrument, and the low-energy charged particle detector. At the end of the science boom is a movable platform that houses the optical sensing instruments, including the incredibly important image science subsystem. The ISS consists of 2 black and white television cameras, a modified version of the slow-scan Vidicon camera designs used in earlier Mariner flights. Also mounted on the platform is the photopolarimeter, a small telescope with polarizing filters to study atmospheric particles, searching for evidence of lightning and auroras. Another instrument, the infrared interferometer spectrometer and radiometer, or IRIS, generates temperature profiles of the outer planets, studies what types of elements are present in their atmospheres, and measures the amount of sunlight they reflect. There is also a specialized ultraviolet spectrometer. On the opposite side of the spacecraft is a 43-foot fiberglass boom nicknamed the Astromast that houses the magnetometers. Its length ensures that the spacecraft's onboard electronics don't interfere with magnetic readings. A smaller boom located below holds the radioactive power source, the RTG. There are 3 of them mounted inline. Each is made of a plutonium-238 fuel source, consisting of small pellets inside that release alpha particles. These particles, which are essentially naked helium nuclei, bombard the inner surface of their containers. This heat is converted into electricity by an array of thermocouples, which is then used to power the spacecraft and its systems. Collectively, they provide 470 watts of power at the beginning of the mission. Over the course of time, the deterioration of wires, thermal contacts, and the radioactive fuel itself will lead to a slow decrease of output. The high-gain antenna is capable of both X and S-band downlink. Data could be stored onboard for later transmission through the use of an onboard digital tape recorder. The belt-driven recorder uses a 328-meter-long reel of 12.5-millimeter wide magnetic tape, recording data onto 8 separate tracks. It could record at a high bit rate of 115.2 kilobits per second and a low bit rate of 7.2. There is conflicting information as to how much data the DTR could actually hold, and this value would decrease over time due to tape errors and hardware aging. At launch, it is believed the tape recording system could hold 536 million bits of information, approximately 67 megabytes, the equivalent of 100 full-resolution photos. 2 whip antennas extending out next to the RTG boom like a pair of bunny ears are the shared planetary radio astronomy and plasma wave subsystem antennas. By this point, the probes are so much more advanced in design and capability than their Mariner ancestors that NASA organizes a competition to choose a new, unique name. On March 4th, 1977, Voyager was approved. On August 4th, 1977, at 12 p.m., NASA releases the official press kit for the Voyager missions. They are to launch aboard a Titan IIIe rocket, also called the Titan Centaur. This massive launch vehicle, with a cryogenic upper stage, is a far cry from the meager Titan IIs that launched the Gemini capsules into orbit, lifting some 15,500 kilograms to low Earth orbit, some 34,000 pounds. This type of rocket had launched the Viking Mars landers in 1975. In the press kit, NASA finally acknowledges that a possible tertiary objective for the Voyager 2 spacecraft will be to fly by Uranus. To this end, Voyager 2 would actually launch first, at the end of August. If lucky enough to obtain the maximum possible performance of the Titan Centaur, it would just barely catch the old Grand Tour window discovered by Gary Flandreau. Assuming it remained healthy, an encounter with Uranus after the Saturn flyby would be a possibility. Voyager 1 would launch 2 weeks later, on a much more fuel-efficient and shorter route to Jupiter. It would actually arrive at Jupiter 4 months ahead of Voyager 2, despite launching later.
I think I was the last person to physically touch the spacecraft. Right during the last step of encapsulation of the spacecraft, we were worried about our fragile windows on our instruments. So I was allowed to crawl up in there, climb up in there and inspect them. And part of the inspection process was to make sure that the little windows were tight on the telescopes. So I gave each one a little twist.
The two Voyagers would arrive at Saturn 9 months apart. If Voyager 1 failed to achieve its Saturn objectives for any reason, Voyager 2 could be retargeted to achieve them at the expense of any subsequent Uranus encounter. It was a compromise. Voyager 2 would serve as a backup to cover Voyager 1's Jupiter and Saturn objectives. Should, however, Voyager 1 be successful in all aspects, Voyager 2 would have the option of a less valuable Saturn flyby, enabling it to visit Uranus. Uranus is mentioned 19 times in the Voyager press kit. Neptune is not mentioned once. But for those in the know, Neptune is right where it would need to be, should the decision come, years down the line, to continue Voyager 2's planetary journey. Officially, however, there is no acknowledgement of anything that smacks of the original Grand Tour idea. In all, there were actually 3 Voyager spacecraft built and given serial numbers, but only 2 were ever planned to be launched. The third was a quarter of a spacecraft at best, to be used as a backup for parts in the event of any unsolvable pre-launch systems failures. And less than a month before launch, failures in 2 of the 3 onboard computers of the Voyager 2 spacecraft result in an ad hoc switch. The spacecraft that would have launched as Voyager 1 is instead bumped up to the earlier slot, and will instead fly as Voyager 2. This will give NASA and JPL approximately 2 weeks to fix the broken computers. If the reversed launch order wasn't already confusing enough, let history record that the physical spacecraft themselves were switched at the last minute to facilitate repairs. NASA has to swap the RTGs as well. Whichever probe launches as Voyager 2 must reserve the option to continue its mission after Saturn. Therefore, one of the 2 sets of RTGs are, for lack of a better term, overclocked. This will enable a longer guaranteed electrical output life. Cups and balls routine complete, the mission is finally given the go for an on-time launch. 2 years to the day after the launch of the Viking mission to Mars, at 10:29:45 a.m. Eastern Daylight Time, the Titan Centaur's 2 massive solid rocket boosters are lit, and there's no stopping them.
Roll program is in on time. Vehicle response is normal. His program was in on time. Vehicle response was normal also. Very smooth flight. Very, very small attitude disturbances.
The entire rocket, spacecraft, and fuel weigh a combined 1.4 million pounds, just over 635,000 kilograms. The 2 solid rocket boosters, which burn alone for the first phase of powered flight, comprising what is known as Stage 0, output nearly double this in thrust.
Normally, vehicle response remains the guidance Data coming back shows that we're right on the money.
For 117 seconds, they spit fire, the combustion products of a nasty mix of powdered aluminum fuel and ammonium perchlorate oxidizer bound together in a polymer known as P-band.
Go ahead.
10 seconds prior to solid motor jettison, the two LR-87 liquid engines of the core stage, known as Stage 1, are jump-started in mid-air thanks to their use of a small solid rocket motor start cartridge.
Shutdown of the solid rocket motors. Start system securing shutdown. Safety 1 is the ignited the Titan Stage 1. The pressures look very good. We have jettisoned the boosters from the Titan.
4 minutes and 20 seconds after launch, staging occurs. The LR-91 single engine ignites and continues carrying the spacecraft higher, faster, and farther towards orbit. 8 minutes after launch, just prior to entering orbit, the LR-91 runs out of fuel. This is planned because the third stage is the real pusher. The Centaur high-energy upper stage, not visible during launch, as it is enclosed within the fairing along with the payload, is different from the two hypergolic liquid rocket stages that precede it, in that it feeds two RL-10 cryogenic hydrolox engines. Like the old Atlas rockets of the Mercury program, the Centaur is a balloon tank. Its structural integrity is derived from the internal pressure of its fuels. Its walls are extremely thin, and this, combined with its incredibly efficient hydrogen fuel, gives it an excellent energy-to-weight ratio. Like the S-4B stage of the Saturn V, the Centaur upper stage burns twice, first to place itself and the Voyager spacecraft into Earth orbit, and then, 42 minutes later, just half of one orbit of the Earth, it fires again. This time it fires much longer, imparting such incredible speed that not even Earth's gravity can hold it back. Voyager 2 is on its way. But the job isn't done just yet. 1 hour after launch, approximately 12 minutes after the conclusion of the second Centaur burn, the Voyager spacecraft separates from the upper stage. It's still got more speed to attain. Attached to the bottom of Voyager is what is known as a kick motor. Officially called the propulsion unit, this represents the last hard punch of Voyager's outbound trajectory. Because it's a solid stage, it can't be shut down or throttled. It imparts a guaranteed velocity increase of 2,000 meters per second, or 4,500 miles per hour. To ensure that Voyager isn't going to overspeed, the Centaur is cut off deliberately early. By the time the propulsion unit delivers its final boost, it's throwing Voyager right down the pipe. A perfect insertion. 4 externally mounted reaction control system pods provide attitude control during the chaotic 43-second final kick. These siphon fuel from the main hydrazine tank located within the Voyager bus. When the Star 37E solid motor finally separates, having delivered on its mission, it takes these RCS pods with it. Voyager itself has an array of 16 smaller hydrazine maneuvering thrusters. These are primarily meant for attitude control and tiny mid-course corrections. Voyager's ability to change its own trajectory, once released from its propulsion unit, is now severely limited. For all intents and purposes, Isaac Newton is now in the driver's seat. Each Voyager probe carries 105 kilograms or 231 pounds of hydrazine fuel for its reaction control system thrusters, pressurized with inert helium gas at 420 psi. 2 weeks elapse as Voyager 2 begins its long coast towards Jupiter. Voyager 1's flight data computer is successfully repaired and reinstalled. Its guidance computer, however, cannot be repaired. It is instead replaced by the one from the third backup Voyager spacecraft, which was simply a proof test model and not originally meant to fly. On September 5th, 1977, Voyager 1 joins its sibling, beginning its journey towards Jupiter. Voyager 1's boost phase was a close one. The LR-91 stage of the Titan III burned for a shorter period than it was supposed to, meaning the liquid hydrogen Centaur stage had to shoulder a bigger share of the burden. 1,200 more pounds of precious hydrolox fuel was consumed than planned. It was a nail-biter. At the moment of the second Centaur cutoff, it was estimated that the stage was perhaps as close as 3.4 seconds away from total propellant exhaustion. Had the same failure occurred on Voyager 2, because of its more fuel-demanding flight profile, the Centaur would have run out of propellant before the probe had reached the proper trajectory, and the solid rocket motor would have been unable to make up the difference. Somehow, by the skin of their teeth, JPL and NASA had squeaked by disaster. Voyager 1 had made it.
Unmanned Voyager spacecraft are en route to Jupiter now. The first Voyager will reach the planet in March 1979, followed by the second spacecraft 4 months later. Then, on to Saturn. At the time of closest encounter, on November 12, 1980, Voyager 1 will have traveled 1.4 billion miles through space.
The Avengers aren't coming to sense today.
Let's do this.
The Voyager spacecraft each carry an optical guidance system that allows them to automatically determine their attitude in space. It's important to know where you're pointed. A sun sensor mounted in the high-gain antenna allows the probe to point itself towards the sun, thus aligning the dish with the inner solar system, and therefore Earth. The body of the spacecraft then rolls until two star trackers, working in a tandem binocular fashion, are able to lock on to a known star based on its unique luminosity. The star intended and most often used for this purpose is Canopus, one of the brightest stars in the celestial sphere. The celestial navigation instruments feed data into the guidance computer aboard Voyager. There are, in all, 3 computer systems aboard this spacecraft. The guidance computer is called HiPACE, or Hybrid Programmable Attitude Control Electronics. It contains 2 redundant plated wire memory banks. Half of each contain fixed memory, and the other half reprogrammable from the ground. HiPACE monitors and controls the sun sensors, star trackers, the movable scan platform on the science boom, as well as a small inertial guidance unit. For short periods of time, should Voyager need to break its optical sun-celestial attitude lock, a 3-axis gyro can measure the drift away from the optic lock point, allowing it to effectively memorize where it's looking. This can be used during periods of scientific observation or instrument calibration. The data those science instruments obtain will be routed through the second onboard computer, known as the FDS, or Flight Data System. This computer controls the science instruments themselves and formats all data for transmission to Earth. Since Voyager will be so far away from Earth during its planetary encounters, the bulk of its motion, where to point its cameras and instruments, when to take readings, and when to transmit, will be loaded onto its computers via ground transmission beforehand. Then, like a player piano, it will dutifully carry out these instructions without hesitation or greater awareness. It is incumbent, therefore, on the Voyager ground team to ensure that the dance they force Voyager to do is proper. One small error in the sequence, and they may forever miss their chance to capture a yet-to-be-discovered moon or snap an image of a fleeting cloud formation. Because these probes will be flying by the planets they are intended to study at breakneck speeds, the time they have to collect meaningful data is measured not in days, but in mere hours. There and gone in the blink of an eye. There is so much at stake. The flight data system and the guidance computer are both controlled by a set of master computers called the Computer Command Subsystem, or CCS. These computers, essentially the same build as the high-pace guidance computer, nonetheless perform a completely separate function. They store and issue the master command of spacecraft sequences, whether that be an attitude maneuver or a series of timed commands to the science instruments. If the guidance and data computers are the instruments in this orchestra, then the CCS is the conductor. Command signals sent from the ground are transmitted through the Deep Space Network system of massive radio telescopes at a rate of 16 bits per second to the spacecraft. There is some minor concern that the science boom aboard Voyager 2 is not latched, as the proper confirmation signal was never sent. However, there is no indication at this point that the boom is loose or in motion. Just 22 days after launch, Voyager 1 is 21 million kilometers from the Earth. On September 16, 1977, it calibrates its camera system by taking an image of the Earth and Moon, both in a single frame. It will be the last time Voyager 1 images the Earth as anything more than a pale blue dot. Through the end of 1977, both Voyagers performed several small mid-course pulses with their hydrazine thrusters, called TCMs, or trajectory correction maneuvers. These are to null out small errors and ensure optimal placement before reaching the critical Jupiter encounter. Minor issues that are common to all space flights develop and are solved during the outbound coast. A slight propellant deficit, a bit failure in one of the CCS computers, sticky motors, and the decision to roll Voyager 2 180 degrees to lock onto the star Deneb instead of Canopus to minimize solar radiation pressure. Things seem to be proceeding normally. It had been planned to observe a near-Earth comet, Kohler, but this was cancelled. There was disagreement amongst the image science subsystem team on whether or not it was prudent to work the imaging system so hard during this early cruise phase of the flight, and also whether or not the brightness of the comet might damage the optics. The spacecraft passes the orbit of Mars in mid-November 1978, and Voyager 1 finally overtakes Voyager 2 on December 15th, now finally worthy of its number. Both spacecraft continue to make leisurely observations of the celestial sphere and our sun, primarily for instrument calibration purposes, though some scientific data is being obtained during this portion of the mission. Small systems failures continue to pop up and continue to be resolved. A frozen scan platform, a stuck filter wheel on the photopolarimeter, a decrease in sensitivity in the plasma experiment. The vicious environment of space takes a constantly growing toll. But then, a major issue develops in Voyager 2. The primary radio receiver experiences an unknown failure which causes excessive current blowing its fuses. For an entire week, all contact with Voyager 2 is lost. A timer in the command computer automatically switches to the redundant backup receiver after not receiving any commands for 7 days. Thankfully, communication with Voyager 2 is re-established. It looks like the primary receiver is busted for good. It will never work again. The secondary receiver thanks to a faulty capacitor in its system, is incapable of correcting for Doppler shifts on the communications frequency. Not only is correcting for these shifts necessary for communication, but measuring the shifts themselves was a way of determining velocity data from Voyager 2, meaning alternate methods of positional navigation would have to be used. For each subsequent transmission to Voyager 2, engineers would have to calculate specific frequencies for outbound communication signals to correct for the Earth's rotation. Yet another headache, yet another burden. If systems continued to fail at this rate, the outlook for an extended mission was grim. JPL's own mission bulletins from 1978 refer to the space probe as beleaguered.
Scariest time was on Voyager 2 when we lost one receiver and found that the backup receiver no longer could tune to the frequency we were sending. So we had to learn how to send the right frequency so the spacecraft could, fortunately we learned how to do that. But that was a very scary period of several months while we sorted out what happened and what the workaround was. But we've flown the entire mission now with this kind of tone-deaf receiver. And so that's fine. There are many such things that happen on real missions. And normally you don't hear about them because once they get fixed, it's sort of old news. So we're very lucky that there's been no catastrophic failure on either spacecraft yet. But you know, that's just the risk of space. I mean, things do happen that you can't fix.
Just in case, Voyager 2's computer is loaded to the brim with commands that would provide for a bare minimum science encounter at both Jupiter and Saturn, should radio uplink be lost for good. Only a year into their mission, both Voyagers have already consumed some 10% of their hydrazine maneuvering propellant, and that was just during the cruise phase. As the scan platform on the end of the science boom slews, it imparts some rotational velocity to the bus. The hydrazine thrusters can then be pulsed to counter this, attempting to keep the spacecraft in as stable an orientation as possible. Nonetheless, some amount of drifting chaos is unavoidable. The narrow-angle television camera, one of two on Voyager, is magnified some 65 times relative to normal human eyesight. Its field of view spans just half of a single degree of the celestial sphere. The scan platform itself has a margin of error of just 1/5 of this. Combine that with the chaotic motion and intermittent drifting of the bus, significant pointing errors resulted. In fact, it was determined that a pointing error of up to 1/3 of the camera's field of view could be expected. This would mean that the position of Jupiter, or any object for that matter, in Voyager's cameras would jump around significantly from frame to frame, meaning significant post-processing and stabilization would be necessary on the ground to create moving sequences. The wide angle was only slightly better, with an 8.7 times relative magnification, its field of view spanning 3 degrees. January 4th, 1979. Voyager 1 enters the observatory phase as it draws ever nearer to Jupiter. The probe begins firing on all cylinders, doing daily system scans across its entire suite of scientific instruments. On January 30th, it begins a 4-day period of intensive Jupiter imaging, returning pictures in real time, shuttering every 96 seconds for 100 hours, capturing 10 Jovian rotations. This is what the unfiltered, unprocessed raw images look like when played back at high speed. All images returned from Voyager are black and white at first. How then are images like this possible? How is color captured with a black and white camera? The answer lies in the filter wheels. Like the photopolarimeter, the television cameras have their own rotating wheel of translucent filters. Green, blue, orange, ultraviolet, and clear. Some of these filters have a scientific purpose, designed to only let specific wavelengths of visible light through, giving an indication of such things as the presence of sodium or methane in the atmospheres of planets. But they can be used for a different purpose as well. If you take 3 black and white images through green, orange, and violet filters, and then dye these images their respective colors in a darkroom on Earth, compositing them will produce synthesized color, an approximation of the general true color distribution of the planet. Every color image from Voyager is in fact a combination of at least 3 separate monochrome exposures, and in some cases more than that. This is essentially a much slower version of the Apollo color television camera, which automated this process in real time at a high rate of speed. So in a way, post-processing has always been a part of Voyager's story. The immense distances it had to transmit data, the relative imprecision of its pointing, and even the errors in its own systems meant that Voyager itself could only show us part of the picture. We humans would have to do the work to piece together the entire puzzle. And that work hasn't stopped since 1979. Many, many years later, with the advent of personal computing, people would come back to Voyager's data, unlocking the secrets embedded in decades-old raster scans. They would apply the powerful new tools of digital processing and photo enhancement to breathe new life into Voyager's images. What Voyager really saw. Take, for instance, the story of Dr. Mark Showalter, who in 1990, using 10-year-old Voyager data, discovered Pan, the 18th and innermost moon of Saturn, a shepherd moon, orbiting within the rings themselves. People like Brian Burns, Ian Regan, Emily Lakdawala, Bjorn Janssen, Ted Strick, and dozens of others who have tirelessly stitched together massive panoramas and have created stabilized moving sequences incorporating color information from both Voyager's own cameras and later missions. Their work makes Voyager's data more accessible and enjoyable to us all. And while the vast majority of them have nothing to do with NASA, JPL, or the official Voyager mission, their contributions are nonetheless an extremely visible part of the historical account of Voyager, occupying a beautiful halfway zone between art and science. The contributions of these individuals and the digitization of these images, showcased here and elsewhere, has led to their rebirth. By late February of 1979, Voyager 1 was in Jupiter's midst. The largest single feature of Jupiter is its magnetic field, the strongest of any planet in the solar system, extending nearly 7 million kilometers in the Sun's direction and reaching the orbit of Saturn in the other direction. It is 20,000 times stronger than that of Earth's, generated by electrical currents in its outer core, composed primarily of liquid metallic hydrogen. Hydrogen, the lightest element in the universe, is normally gaseous, but when placed under conditions of extreme pressure, it liquefies and can act as an electrical conductor. This means that Jupiter's magnetic field is the product of an entirely different mechanism than Earth's, which is produced primarily by a mixture of molten iron and nickel. Jupiter's magnetic field is blunted and shaped by the solar wind, the supersonic stream of particles and radiation pressure given off from the Sun. This effect is common across all the magnetically active planets. However, as Voyager 1 streams through the Jovian system, it encounters something wholly unexpected. A massive ring of plasma around the planet composed of sulfur and oxygen ions. The plasma torus in Jupiter's equatorial plane co-rotates with the planet, causing a deformation of the magnetic field into a flattened, pancake-like disk. Electrons within the plasma generate a strong radio signature, with short, superimposed bursts, making Jupiter appear like a radio pulsar. Not counting its core, Jupiter is somewhere between 87 and 92% hydrogen, another 8 to 12% helium, and the rest is methane and ammonia with trace elements. It is 11 times larger than the Earth by diameter, 1,321 times larger by volume, and has 318 times more mass. A gas giant, it lacks a solid surface, though it is believed to have a solid, rocky core. Its appearance is a swirled mix of tans, browns, and oranges. The outer atmosphere is subdivided into latitude-oriented jet streams, with altering regions of lighter-colored zones and darker-colored bands. The orange and brown colors are caused by upward-moving material from below that react and change color when exposed to sunlight. The light-colored zones are richer in crystallized ammonia clouds that hide the deeper, darker material below. The planet spins once on its axis every 9 hours and 55 minutes. The counter-rotating jet streams in its atmosphere create vortical storms along their borders. There are dozens of these storms at any one time, spread out across the entire planet. But none are as big, or as famous, or as old as the Great Red Spot. A cyclone is defined as a large-scale circulation of winds around a central region of low atmospheric pressure. By contrast, an anticyclone is a similar circulation of atmosphere around a region of high pressure. Knowing this matters because anticyclones, which the Great Red Spot is, have a clearing effect of clouds and high-level moisture. This means that the Great Red Spot is not an object, but a hole. It allows us to peer deeper inward. Wind speeds of 432 kilometers per hour are produced along its edge, and the diameter of this one Jovian storm is greater than that of our entire planet. The first official sighting of the Great Red Spot from Earth-based telescopes was in 1831 by German astronomer Heinrich Schwab. It was observed periodically throughout the 19th century. It may have been spotted as early as 1665 by Englishman Robert Hooke. Volume 1 of the Philosophical Transactions of the Royal Society, page 3, refers to a, quote, spot in one of the belts of Jupiter, though he could have been referencing one of Jupiter's 4 large innermost moons discovered in 1610 by Galileo Galilei. While the precise date of this ancient storm's discovery is controversial, what is beyond dispute is the fact that it is shrinking. It's only half as large today as it was in the 19th century, its future uncertain. Perhaps it will disappear in our lifetimes. Perhaps it will experience a resurgence and grow again. Jupiter's mass is 2.5 times that of all other planets in our solar system combined. So massive that it causes our sun to appreciably wobble. The center of gravity between Jupiter and our star lies outside of our star's surface, meaning in effect the two orbit each other, though just barely. As Jupiter radiates heat and energy, it cools and shrinks. It is believed to be the oldest planet in the solar system, and when it formed, it was much hotter and nearly twice the size it is today. Jupiter would need to be approximately 75 times more massive for conditions within its core to achieve the proper temperatures and pressures to fuse hydrogen and become a star. Most stars in our galaxy are in fact binary systems, with up to 85% of the star systems in the night sky composed of 2 or more individual stars. Single stars, like our own sun, are the exception, not the rule. Jupiter would have been a companion star, but it failed to attain enough mass. As Voyager 1 speeds past, it turns its attention to Jupiter's moons. In 1979, Jupiter had 14 known satellites. Thanks to the Voyager spacecraft and others that would come in the future, such as the Galileo mission, Jupiter now has over 80 known satellites, and that number continues to climb. Most of these satellites are simply small asteroids, but 4 stand apart. These moons, discovered in 1610 by Galileo, bear his name as the Galilean moons. Each one of them a massive, incredibly unique world. Do you remember the torus of plasma mentioned earlier that significantly deforms Jupiter's magnetic field? This cold, dense plasma slowly moves outward, sapped and transported by Jupiter's magnetic field, and then ultimately carried away by the solar wind. Something is replenishing it from within. The answer to that mystery was discovered by Voyager 1 and has to do with Jupiter's innermost Galilean moon, Io. When Galileo first observed Io on January 7, 1610, it was not identified as its own body until the following night, January 8th. For the next 2.5 centuries, it was little more than an unresolved, 5th magnitude point of light in astronomers' telescopes. It wasn't until the mid-20th century that telescopic observations began to hint at Io's unusual nature. Analysis of the wavelength of light reflected from Io hinted at a surface dominated by evaporates of sodium salts and sulfur dioxide. Io orbits Jupiter at a similar distance that the Moon orbits the Earth, some 350,000 kilometers from its cloud tops. But what makes Io truly special is its geologic activity. Io experiences such tremendous tidal forces from Jupiter's gravity that its insides are literally churned. It has some 400 active volcanoes, and through these, it explosively spews out its insides at a rate of at least 1,000 kilograms, a metric ton, every second. These volcanic ejections are dissociated into atomic ions and are swept up by Jupiter, trailing behind Io like a massive tail. The plasma torus is composed of matter ejected from Io, and for outer space it's surprisingly dense, at some 500 atoms per cubic centimeter. It is in fact small eccentricities in Io's orbit that causes such an extreme flux of felt forces, and this non-stop expulsion of matter and energy would, under normal circumstances, eventually allow Io's orbit to circularize. However, Io is unable to circularize because of 2 other Galilean moons, Europa and Ganymede. These moons are in resonance with Io, meaning they experience periods of proximity at regular intervals at the same point in space, time and time again. These encounters, with the other moons on one side and Jupiter on the other, are tearing Io apart. It is a tortured existence, but one which has a profound effect on the Jovian system. Io is tidally locked to Jupiter, meaning one side always faces its parent. Scientists suspected Io's surface would be pockmarked with craters, but instead they find it's almost completely lacking, covered in smooth plains dotted with tall mountains, pits, and volcanic lava flows. A variety of colorful features thanks to various sulfuric compounds. Voyager 1 observes at least 9 active volcanoes and photographs several mid-eruption.
Before Voyager, the only known active volcanoes in the solar system were here on Earth. And then Voyager flew by Io, a moon of Jupiter, about the size of our moon, but 10 times the volcanic activity of the Earth. Quite a striking change to realize the Earth was no longer the most volcanically active body.
As Io cuts across Jupiter's inner magnetic field lines, it develops some 400,000 volts across itself and creates an electric current of some 3 million amps. This current creates what is called a flux tube, traveling along the magnetic field to the upper atmosphere of Jupiter, where it accelerates charged particles into the atmosphere, creating a visible, concentrated bright spot within Jupiter's permanent polar auroras. An electron rain, contributing to powerful polar lightning within Jupiter's clouds. You heard me right. Io is at least partially responsible for lightning on Jupiter. Voyager 1 experiences 1,000 times the lethal dose of radiation for humans as it passes between Jupiter and Io. Constant volcanism, intense radiation, and powerful electric fields make Io an unlikely destination for life. But this is where Voyager turns its attention instead to the second Galilean moon, Europa. Voyager 1 does not get the opportunity for a close-up at Europa, but 4 months later, Voyager 2 will. With a diameter of 3,100 kilometers, Europa is slightly smaller than our moon. Its surface is a chaotic crisscross of icy lineae. Its composition, mostly water ice, frozen at negative 138 degrees Celsius, negative 216 degrees Fahrenheit. At such low temperatures, the water ice here is as hard as granite. The brownish, reddish regions are also water ice, though they are dirtied with clay-like materials and salts. Despite its striking terrain features, Europa lacks mountains and craters, making it the smoothest object in the solar system, though it is possible that regions of its surface are covered in icy spikes that resemble stalagmites. On a large scale, it appears that Europa's crust is moving. The cracks that permeate its surface are evidence of shearing, caused in part by tidal flexing exerted by Jupiter and the other Galilean moons. Unfortunately, there's a problem. Because Europa, like Io, is tidally locked to Jupiter, the cracks on its surface caused by tidal flexing should form a distinctive and predictable pattern. Yet this is not the case. Somehow, the crust is rotating. Just as tidal forces melt rock within Io, could those same tidal forces be melting ice within Europa? There are very few impact craters, suggesting that some type of resurfacing mechanic is at work. It is believed that the cracks behave much like tectonic plate boundaries on Earth, with crust material subducted below and new material diverging upward. The scientific consensus is that a layer of liquid water or soft ice exists beneath Europa's surface, and that this drives the mechanical separation and motion of the outer crust. The size of this subsurface ocean is unknown, as is conclusive evidence of its existence. Unfortunately, even the smallest estimates put Europa's solid ice crust at several kilometers thick, well beyond the deepest we have ever drilled on Earth. Still, there are those who dream of the day we might land on Europa and bore down into a warm, saltwater ocean full of hypothesized alien life. Indirect observations of Europa hinted at plumes of water vapor, though these are likely caused by the bursting of pressurized briny water pockets near its surface. There is some level of matter being emitted from Europa, and cryovolcanism is the likely cause, but it is not yet clear if this is correlated to its hypothesized subsurface oceans. When the Voyager probes and the later Galileo mission encountered Europa, the possibility of life within caused an explosion of excitement. Since then, discoveries around other moons elsewhere in the solar system have surpassed even Europa in potential habitability, but it nonetheless remains one of the highest priority targets for the seeking out of life elsewhere in our solar system.
When we think of places you might find life, we typically think of the Goldilocks zone around a star, where water would be liquid in its natural state. And if you get a little too close to the star, heat would evaporate the water. Too far away, it would freeze. And neither of those states of H2O are are useful to life as we know it, we need liquid water. So you can establish this green zone, this habitable zone, this Goldilocks zone, where if you find a planet orbiting there, hey, there's a good chance it could have liquid water. Let's look there first for life as we know it. Now, it turns out that this source of heat, of course, is traceable to the sun. And if you go farther out, everything would or should be frozen, all other things being equal. But Europa, a moon of Jupiter sitting well outside of the Goldilocks zone, is kept warm. Not from energy sources traceable to the sun, but from what we call the tidal forces of Jupiter itself. So Jupiter and surrounding moons are actually pumping energy into Europa. And when you do that to a solid object, the solid object is stressing. So you have this frozen world, Europa, completely frozen on its surface. But you look at the surface and there are cracks in the ice. And it shifted and then refroze. So this ridge has a discontinuity in the crack and then continues in another place. So what this tells you is that Europa cannot be completely frozen. Because if it were, nothing would be moving. You look at the surface of Europa, the frozen surface, there are like ice chunks that are like shifted and refrozen and shifted again. It looks just like if you fly over the Arctic Ocean. Fly over the Arctic Ocean in the winter, these are ice sheets that are breaking and refreezing all the time. It's the same signature as that. So all of us are convinced that beneath this icy surface is an ocean of liquid water. And there's no reason to think it wouldn't have been liquid for billions of years. On Earth, where we find liquid water, we find life.
Ganymede, the third Galilean satellite, orbits at a distance of just over 1 million kilometers. Like Io and Europa, it's tidally locked. Because Ganymede's eccentricity is low, tidal heating is negligible. However, in the past, Ganymede may have experienced isolated episodes of tidal heating as a result of its orbital resonance with Io and Europa. Ganymede is the largest and most massive moon in the solar system, larger even than the planet Mercury, though far less dense, clocking in at under half of Mercury's mass. This suggests a composition of equal parts rocky material and ice. The Galileo mission would, in the 1990s, conduct magnetic measurements of Ganymede that recorded a significant, persistent magnetic field around this moon. This suggests that Ganymede's core is not frozen. Yet, for an object of Ganymede's low density, there should not be enough iron to generate such an active magnetic presence. Furthermore, Ganymede's magnetic field is constantly shifting. Somehow, it's being amplified. The leading model suggests that, like Europa, Ganymede may have a massive subsurface ocean, the fluid motion of saline water acting as a conductor below the surface. That is, of course, just one theory. Like with Europa, there is no direct evidence of a subsurface ocean on Ganymede. But if the saltwater model happens to be true, then Ganymede's ocean would have to be incredibly large. A global layer somewhere between 100 and 800 kilometers thick, it would be the largest ocean in the solar system, bar none. Loads more than all the water on Earth. There are lots of possible models for Ganymede's interior. Don't get too excited though. If it does exist, it's trapped 95 kilometers below a crust of rock and ice. Scientists are unsure how Ganymede got its grooved terrain, which appears similar to Europa's. This suggests tidal heating, but that would be improbable given Ganymede's distance from Jupiter. Perhaps it formed much closer and migrated outwards. Ganymede's surface is considerably older than Europa's and is covered in impact craters. The surface radiation experienced on Ganymede from Jupiter is enough to cause severe illness and death after just 2 months. Before the Voyager missions, it was believed that Ganymede and the fourth Galilean moon, Callisto, were incredibly similar. Both are larger than the planet Mercury, both are relatively dark, and both are very lightweight. There, however, the similarities begin to end. Voyager 1 reveals that Callisto has perhaps the most ancient surface of any moon or planet in our solar system. Countless impact craters, the result of meteorite bombardment over 4 billion years, kept in a state of complete preservation. Ganymede's surface may only be a quarter as ancient as Callisto's. There is no evidence of any endogenic processes occurring on Callisto now or in the ancient past, such as volcanism or tectonic activity. As mentioned, its low density suggests lots of ice. Whether or not this ice is partially molten at some deep subsurface layer is hard to say. Once again, certain models support the possible existence of a salty underground ocean based entirely on magnetic data that suggests Jupiter's own magnetic field creates electrical currents within Callisto. This may imply a layer of highly conductive fluid within. There is simply not enough good corroborating data to qualify this interpretation, which is one of many. A significant problem with this theory is that Callisto experiences no tidal heating of any kind, meaning if there is a thick layer of ice, it is likely completely frozen solid. Perhaps the radioactive decay of heavy elements deep within Callisto's mantle provides the heat. The question is whether or not the moon as a whole is insulative enough to keep that heat from simply escaping through its crust and radiating outward into space. Once again, we lack enough information. One thing that makes Callisto an interesting exploration target is the fact that it experiences very low levels of Jovian radiation on its surface. For those with minds inclined towards science fiction, or perhaps just boundless ambition, Callisto is an ideal base for a human outpost. The richness of water ice on its surface holds the promise of drinking water, breathing oxygen, and the production of rocket fuel. As Voyager 1 transits Jupiter's equator, a thoughtfully programmed maneuver points its television cameras out into space across the equatorial plane and exposes it for an incredible 11 minutes and 12 seconds. The sheer length of this exposure is almost unheard of. NASA is searching for something incredibly dim. The squiggly lines you can see are in fact stars. They look the way they do because their light on the camera's sensor has been recorded for over 11 minutes. The spacecraft's natural oscillation, as well as its rapid speed as it flies by Jupiter, has dragged these points of light across the image frame. But that isn't what this photo is showing us. Look instead at the large band diagonally dissecting the center of the image. That is the first ever visible proof of rings around Jupiter. Jupiter's rings are incredibly faint and composed of thin, dark dust. Only one, called the main ring, is even remotely well defined. It is believed that these rings are formed from meteoroid impacts with Jupiter's moons, careening off streams of fine particles into its orbit. Its overall age is unknown, but it is believed that the average dust particle spends no more than 1,000 years in the ring before being sapped away by a number of external forces that act as a drain on the ring itself. Therefore, it must be constantly replenished by new impact events. Jupiter's rings may be faint and tenuous, but they are there. The 2 Voyager spacecraft greatly expanded our body of knowledge of the Jovian system, setting the stage for future missions to build upon their success. 3 new satellites were discovered, and a massive host of data was obtained that allows us to characterize this planet and the moons we knew existed but knew nothing about in great detail. Despite the earlier problems experienced during the coast phase, the Voyager mission at Jupiter was a tremendous success. So successful, in fact, that it would have an impact on another mission still ongoing. It was time for JPL to exact their revenge.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done in a list view. Next, I set a priority and a due date.
The half-ton Pioneer 11 probe, which had encountered Jupiter in 1974, was still traveling outwards towards Saturn and would reach its closest approach in September of 1979, just a couple months after the Voyager probes had rounded the fifth planet and were well on their way to the sixth. The two Pioneer probes, 11 and its sister 10, were a small part of the reason that Grand Tour was originally canceled. Now, JPL was in a position to exert its will on NASA's Ames team, responsible for Pioneer. Since Voyager 2 was still on a Grand Tour trajectory, JPL argued that Pioneer 11 should be retargeted to fly through Saturn's outer A ring, something that Voyager 2 would have to do in order to be successfully retargeted towards Uranus. JPL wants Pioneer 11 to be a test dummy, sacrificing some of its own scientific objectives to act as a mere forerunner for Voyager. Scientists are unsure of the makeup of the rings at this point and are worried that the spacecraft might be impacted and destroyed by the material within. JPL and the Voyager team, who were unaffiliated with Pioneer, were adamant that the smaller, less sophisticated probe test the route that Voyager 2 would have to take. The Pioneer team, for their part, argued that the outer path would be too far away from Saturn for their spacecraft to take the measurements that scientists were interested in. For the first time in this story, NASA management sides with JPL. They concur that Pioneer at this point is a mere prelude to Voyager, and to the sound of much booing from the Pioneer team, Director of Planetary Programs Tom Young announces to the public that Pioneer 11 would travel through the outer rings, less as a trailblazer, more as a guinea pig. The Voyager team would know soon enough whether passage through the outer ring was feasible. They continued to hold on to hope for their extended mission. Pioneer 11 passes Saturn on September 1st, 1979. It nearly collides with a previously undetected moon, missing by just 2,100 nautical miles, some 4,000 kilometers. It discovers another previously unknown moon and charts Saturn's magnetic field. NASA had given it a 50-50 chance for survival, and yet Pioneer 11 passes through the ring plane unfazed. Saturn's rings are nearly 300,000 kilometers across and impossibly thin, high estimates placing them no more than 100 meters or 330 feet in width. Low estimates as thin as just 20 meters or 66 feet. It takes Pioneer 11 just 4/5 of 1 second to traverse through the rings. Pioneer 11 may have been primitive compared to Voyager, but its importance as the first man-made object to reach and study Saturn cannot be overstated. Saturn's equator and rings are tilted 27 degrees to the plane of the ecliptic, giving rise to seasons. The sun illuminates the northern face of its rings for one half of the year and the southern face for the other half. Given Saturn's incredible distance from the Sun, it takes 29 Earth years for it to complete one full orbit, and thus its 2 seasons last 14.5 years each, its rings acting like a massive sundial, casting varying degrees of shadows on its atmosphere. 1979 happens to be a year when Saturn's rings are in near alignment with the Sun, meaning the shadow they cast is minimal. Missions sent decades later, such as Cassini, would capture a wholly different view. The 2 Voyager probes are traveling much faster than Pioneer 11, and unlike it, they would not take 5 years to reach the planet. In fact, Voyager 1 would encounter Saturn just 21 months after it had left Jupiter. Both Voyager probes experienced glitches and hiccups as a result of the intense radiation around the fifth planet, including, but not limited to, clock errors, photographic artifacting, and communications troubles. However, as they speed away from Jupiter, they appear more or less unharmed. During an attempt to put Voyager 1 into a Sun-Canopus alignment, its star trackers accidentally lock onto Alpha Centauri, resulting in a temporary loss of downlink. Voyager 2's polarimeter experiment may have suffered irreparable damage at Jupiter, with a definite issue in its filter wheel. Voyager 1's polarimeter had died completely, after tests indicated that it had lost all sensitivity to light. It is the first scientific instrument between the two probes to be shut down permanently. It will not be the last. Voyager 2's backup mission load, which had been programmed into its computer ever since it lost its primary radio receiver, is amended now that it has passed Jupiter. Its secondary receiver continues to work well, but JPL remains vigilant. The outlook for the Uranus encounter looks better and better. Voyager 1 begins its concentrated observations of Saturn in late August of 1980 and will pass by the planet in November. Voyager 2, now 9 months behind, will follow in 1981. One major discovery is made right off the bat. Voyager 1's planetary radio astronomy experiment conclusively measures that Saturn spins once on its axis every 10 hours and 39.5 minutes, give or take a few seconds. The equatorial regions of its atmosphere can rotate as fast as 10 hours and 14 minutes, indicating the presence of high-velocity jet streams. Don't let Saturn's pale hues deceive you. Wind speeds can reach 500 meters a second. That's over 1,000 miles an hour. Saturn is a blender. Aggressive mixing has eliminated most of its definition, but faint bands are still visible. Of course, the most prominent and obvious Saturn are its rings. Saturn is the jewel of the solar system. Once again, Galileo can be credited with having first sighted them, but others were the first to correctly deduce what they were. Galileo described the planet as having arms. Decades later, Dutch astronomer Christian Huygens identified them as rings in the 1650s. And in the 1670s, Italian-born, French-naturalized Jean-Dominique Cassini first described the structure of the rings, citing the largest gap which now bears his name, the Cassini division. Saturn's rings boast incredible structure and complexity. They are mainly water ice, carbon, and organic compounds. There is more to Saturn's rings than meets the eye. Visible only in up-sun photographs, Saturn's G and E rings appear as faint glows encircling the planet, but it doesn't stop there. At a distance of some 12 million kilometers is arguably Saturn's strangest ring, the Phoebe ring, named after the small moon that matches its orbit and from whom it likely originates. The Phoebe ring is not only massive and nearly invisible, it's tilted significantly, and what's more, like Phoebe itself, it orbits retrograde, opposite to the spin of both Saturn and all its other moons. The original theory behind Saturn's rings is that they are leftover material from the original planetary nebula from which Saturn was formed. Surely, what is happening now has always happened and will always continue to happen. Could this be a cosmic hot hand fallacy? Data from more recent missions, such as the massive Cassini orbiter, suggest that they are instead no more than 100 million years old, meaning that they could have formed around Saturn as a result of impacts between two or more of its moons at the same time that dinosaurs roamed the Earth. Furthermore, material from the rings are being drained by its magnetosphere at an alarming rate. They may have less than 100 million years to live. Nevertheless, for the short term anyways, the rings are highly differentiated, highly structured, and highly stable. They are kept in place by the influence of small, so-called shepherd moons that orbit amongst them, keeping them in gravitational balance and preventing their spread and dilution. The Voyagers spot another curiosity in the ring, some kind of deformation in the pattern. These artifacts, nicknamed spokes, are likely caused by Saturn's magnetosphere, electrostatically interacting with very fine magnetic dust particles within the rings, causing them to clump together and behave abnormally under the influence of Saturn's powerful interior forces. Saturn, unlike Jupiter, is not reddish in the slightest, though as far as composition is concerned, the two are very similar. Both are predominantly hydrogen. Saturn is around 96% compared to Jupiter's 89%. Saturn has less helium, 3.5%, but both have trace amounts of methane and ammonia. It is still uncertain to what extent Jupiter's red colors are a function of chemical reactions localized entirely within its atmosphere, possibly involving sulfur compounds, or whether they are reactions with solar radiation. Either way, this process does not appear to take place on Saturn. It is largely monochromatic, with various hues of pale yellow. Like in Jupiter's yellowish zones, the color is thought to originate from clouds of crystallized ammonia. It has been theorized that below the upper atmosphere exists a series of relatively long-lasting dark belts and light zones on Saturn. One does not have to penetrate very deep into Saturn before its hydrogen is compressed into a liquid. Liquid hydrogen is believed to be its thickest layer, making up for well over half of the planet by volume. Deeper in, this hydrogen begins to take on metallic properties and may even be compressed into a solid. Saturn has a hot, rocky core. The planet radiates 2.5 times more energy out into space than it receives from the Sun. Because of the unique combination of its massive size and rapid spin, Saturn is the most squished planet in the solar system. Its polar radius and its equatorial radius differ by nearly 10%. Saturn and Jupiter together hold 92% of all of the planetary mass in our solar system. Storms do occur on Saturn, though they are short-lived and difficult to catch. When they do happen, they appear as milky white fluid turbulence permeating across the otherwise featureless, banded face of the pale planet. Saturn's incredible winds are responsible for two of the solar system's greatest oddities. At its south pole, a fantastic, hurricane-like vortex nearly the size of the Earth that may have existed for billions of years. At its north pole is something far, far stranger. Perhaps the weirdest demonstration of fluid dynamics anywhere in the solar system, a permanent hexagonal cap. Its alien appearance seemingly defies logic. It is unlike anything we have ever seen on Earth. The change in relative wind speeds across Saturn's latitudes are the cause. Adjacent parts of Saturn's atmosphere moving at different speeds induce unstable behavior, in this case, a wave-like disturbance. This shape and others have been recreated in labs on Earth using nothing more than water, flow gradients, and fluorescent dye. Not so alien after all. Another oddity with Saturn is its magnetic field, which seemingly defies classification. On Jupiter and Earth, the magnetic fields are offset from the rotation axis by around 10 degrees. The traditional logic holds that this tilt is a natural byproduct of how the magnetic field is generated, from currents deep within the planet's interiors. Without some level of interior turbulence, the magnetic fields wouldn't exist. It's the fact that the core is not perfectly aligned with the exterior in both spin and spin rate that generates this flux. Saturn, however, defies this. Its magnetic field is almost perfectly aligned with its rotational axis, perhaps down to just half a degree. Likely for this reason, Saturn's magnetosphere is fairly weak for a planet of its size. While its magnetic field is 600 times the size of the Earth's, overall it is slightly weaker. Saturn is surrounded by a myriad of unique and interesting moons. And thanks to later missions like the Cassini orbiter, we are aware of more moons around Saturn, some 83 and counting, than we are around Jupiter. That isn't to say, of course, there are more, but the quality of our data around Saturn, thanks to Cassini, has surpassed that of our data around Jupiter. The Voyagers observed several of Saturn's incredible moons as they speed through its system. There are, of course, the asteroid-like shepherds of the rings, Pan, Pandora, and Prometheus, Janus, and Epimetheus. These moons are interesting in their own right, but perhaps more so because of the utility they play in maintaining Saturn's stunning cosmic appearance. Further out, of course, you can't miss Mimas, believed to be responsible for the Cassini division. It has a massive impact crater on its leading edge, giving it a Death Star-like appearance. Further out, you reach the E-ring, that mystical outer glow only visible when looking towards the sun. Within the E-ring orbits a small, icy moon called Enceladus. In 2005, decades after the Voyager flybys, the Cassini probe would discover the connection. Long suspected and finally confirmed, Enceladus has multiple jets of material emanating from its south pole, geyser-like plumes of warm, salty water. Enceladus is ejecting massive amounts of salt water laced with grains of silica-rich sand, nitrogen, and organic molecules, including trace amounts of simple hydrocarbons, to the tune of some 200 kilograms or more every second. The two Voyager probes imaged the northern face of the small moon and missed the geysers, which are almost entirely concentrated near its south pole. However, the fact that Enceladus was embedded in the densest part of the E-ring led many to conclude that the ring was a product of material vented from the moon. Few could have imagined, however, that this material would be ideal for life as we know it. The water coming out of Enceladus's geysers isn't just full of organic compounds and silica sand and simple hydrocarbons. Perhaps most importantly, it's warm, full of thermal energy. The source of this energy is not fully known, since tidal heating can only account for some 10% of it, if that. Enceladus is very, very small, with a diameter of just 313 miles, or just over 500 kilometers. Its tiny size and gravity rules out the possibility of a molten core or the presence of heavy, radioactive elements deep within. These may have been a factor during its initial formation, but the mystery remains. How has it maintained its heat energy for so long? Direct evidence of warm water geysers originating from a subsurface ocean places Enceladus at the top of the pile in terms of places where life is likely to exist outside of Earth, surpassing Mars and even Europa. Further from Enceladus is icy Tethys, itself covered with impact craters ranging from the small to the colossal. Then, of course, there's rugged Dione, covered in scars and canyons, a world riven by enormous fractures on its trailing hemisphere. As you continue moving outward, the moons seem to get larger. Further still from Dione is its bigger twin, Rhea. Each of these moons an icy, desolate world, their surfaces logging an ancient history of impacts and interactions with rings and debris. But from here, things take a dramatic turn. 750,000 miles away, some 1.2 million kilometers out from Saturn, exists its largest and most complex moon. A moon that stands apart, not just in the Saturn system, but in the solar system. For hundreds of years, it was known as a fuzzy orange ball, featureless, mysterious, unknown. Titan is the only moon in our solar system with a real atmosphere. An atmosphere so thick, that despite having a surface gravity only slightly less than that of our moon, the atmospheric pressure at Titan's surface is 1.5 times greater than that of sea level on Earth. In short, Titan has a lot of sky. And because of its low gravity, that atmosphere does not cling to its surface as tightly as Earth's does. Instead, it hangs loosely around the moon like a thick outer shell. Because atmospheres get progressively thinner, it's nearly impossible to define a strict upper bound. What you, I, and human law commonly thinks of as space, low Earth orbit, is actually well within its scientifically defined atmosphere. And this is why the ISS, which orbits within the thermosphere layer, requires periodic boosting. But to give you an idea of how much higher Titan's sky rises above its surface, understand that the opaque orange haze that obscures its surface exists at or slightly above an altitude of 200 kilometers. That's over twice as high as the internationally recognized boundary of space, the Kármán line on Earth. And that layer of haze is considered one of the lower layers of Titan's atmosphere. The 2 Voyager probes make valuable observation of Titan in their time, but the details of its surface will remain locked away until, of course, Cassini and a small stowaway on its side, Huygens, in the mid-2000s. The Huygens probe separated from the Cassini orbiter and became the first spacecraft to enter Titan's atmosphere, successfully landing on its surface on January 14, 2005. In an ironic twist of fate, a design flaw with Cassini's radio relay firmware led to an issue with Doppler-shifted data transmitted from Huygens, not wholly dissimilar from the issue that plagues Voyager 2. As Huygens descended, it transmitted data over 2 radio channels. Due to a ground sequencing error, Cassini was not listening on one of the 2 frequencies, meaning half the data transmitted from Huygens was lost. Despite being plagued with problems compounded by human error on the ground, the small probe returned the first images of Titan's surface and made invaluable measurements of conditions on the ground. Titan is an incredibly cold world. The temperature at the landing site 180 degrees below 0 Celsius, nearly 300 below Fahrenheit. Amazingly, it's a humid world and has stable bodies of liquid on its surface. There's lakes, clouds, and even rain. Titan has weather. It has a climate. It's liquid methane. Titan's atmosphere is over 95% nitrogen gas, but the haze and humidity is from methane gas, 1.5% at high altitude and nearly 5% near the surface. Titan's methane cycle is amazingly similar to Earth's water cycle. It evaporates, rises, condenses, and rains. Methane lakes on Titan are similar in size to the American Great Lakes. They are the only stable bodies of liquid on the surface of a celestial object outside of Earth. Below its opaque haze, Titan has wispy methane clouds. Most of its lakes are concentrated near its poles. These lakes are dark, highly reflective, and very, very cold. There's no risk of fire here, because there's no concentration of oxygen here. Titan has hundreds of times more liquid hydrocarbons than all known oil and gas reserves on Earth. But unlike on the Earth, these formed abiotically. Likely a result of ultraviolet radiation from the sun, which knocks hydrogen atoms off of stable methane molecules in the atmosphere to form highly reactive methyl radicals that then react with each other to form more complex compounds like ethane and propane. Endless combinations of carbon and hydrogen that together make up a vast, complex climate on Titan. Conditions on Titan's surface are very close to the triple point of methane, meaning it can coexist as a solid, gas, or liquid, and tiny variations of energy and pressure across small distances can result in phase changes. The exact composition of Titan's lakes are unknown, but it is believed they are a mix, storing the concentrations of the heavier hydrocarbons like propane and ethane, along with a bulk volume of liquid methane. It's even possible that solid methane ice, full of nitrogen gas bubbles, could be floating on the surface of these lakes, but this has not yet been confirmed. The rate of evaporation on Titan is incredibly low, but its thick atmosphere can hold a lot more liquid before rain forms, aided by low gravity. As a result, it is believed that Titan experiences long periods of relative drought, lasting decades or perhaps centuries, followed by torrential hydrocarbon rains and flash floods that impact the surface on a global scale.
And then we flew by Titan, which is the fuzzy ball you see here, which has 50% higher pressure nitrogen atmosphere than here on Earth, but has methane, natural gas, in the atmosphere, not oxygen. So the action of sunlight is to create complex organic molecules which create this haze that cannot be seen through in the visible. Fortunately, the Cassini mission appeared several decades later with a radar system that could look through the clouds, through the haze, and saw that indeed there are lakes of liquid methane, liquid natural gas on this moon, perhaps resembling what the early Earth may have looked like before life evolved.
Observation of Titan was considered a key objective for Voyager 1. So much so that its trajectory around Saturn, optimized specifically for proximity to Titan, prevented it from continuing on to Uranus or Neptune. This is where the journeys of Voyager 1 and Voyager 2 diverge. Throughout the mission, it remained a possibility to retarget Voyager 1 away from Titan and instead use Saturn's gravity to throw it towards Pluto, and it would have arrived in 1986. Instead, Titan was deemed a much more valuable exploration target, and Pluto would remain unvisited until the New Horizons probe flew past it in 2015. This was the ultimate moment of decision. Had Voyager 1 failed to image or make measurements of Titan, Voyager 2's extended mission would be cancelled, and it would be retargeted towards the small moon. But luck was on JPL's side. Voyager 1's Titan observations were deemed satisfactory, and Voyager 2 remained on its grand tour path. Voyager 1 is flung above the plane of the ecliptic by Saturn, on a journey that would not take it near any planets ever again. As it leaves the Saturnian system, it photographs the outer satellites, multicolored Iapetus, stained from ring material, and the elusive retrograde Phoebe, orbiting within its own faint ring that would remain undiscovered for decades.
It's always gratifying to have the results be something more than what was expected, and Saturn and what we have found was not expected.
I suspect even for the next few years, we will find new discoveries in the data which we've acquired in the last few days.
And as we see more and more examples of the way the universe can put planets together, we find that our terrestrial perspective in explaining our own planet has been rather limited. We get new ideas from this.
What we learned about Saturn during that encounter and during the months that preceded it have really rewritten the textbooks on Saturn.
The Voyager probe's encounter with Saturn were far from definitive, but they provided a first glance at the environments that missions like Cassini would later study in detail. By January of 1981, the planetary exploration phase of the Voyager 1 spacecraft had ended. No more worlds lie before it. However, it was not shut down or turned off. Now testing the interplanetary waters, it continued on, studying the sun as it began a long, open-ended mission out of the solar system. Because of the encounter with Jupiter and Saturn, it was now too far and traveling too fast for the sun's gravity to hold it in. Scientists were pretty confident that our sun's magnetic field, though much, much stronger, was fundamentally similar to the magnetic fields of the planets. They knew at some point the particles streaming outward would bend and arc backward, blunted by the interstellar wind, the combined radiation pressure of all the other stars in our galaxy. In 1981, JPL hypothesized that Voyager 1 might cross this boundary in 1990 at a distance of 40 AU, 40 times the distance between Earth and the Sun. They had no idea how large our meager star's influence really is. Voyager 1 would not cross this boundary until it had reached a distance of 122 AU, or 18 billion kilometers away in 2012. By then, an entirely new generation of scientists had matured and were working with Voyager, many of them too young to remember a world before its discoveries. Mapping and measuring the outer layers of our star's magnetic field and how the solar wind interacts with the galaxy is the underlying principle of the Voyager interstellar mission, which continues to this day.
The magnetic field lines are showing us how the magnetic field is wrapping around this heliopause surface, and we believe that what Voyager is telling us is as it propagates farther away from the sun, it's going to tell us more about how far this interaction goes.
But then the magnetometer people came along and said, but you know, the magnetic field direction didn't change at all. So that would mean that the sun's magnetic field and the galaxy's magnetic field were lined up. And that didn't seem likely. Then the plasma wave team came to the rescue. The sun sent out some big blast waves, had sent out some big blast waves, and they reached the vicinity of Voyager 1, and it caused the plasma to oscillate. And the plasma wave experiment measures the frequency of those oscillations. And it turns out if you know the frequency of those oscillations, then you know the density of the plasma. And it turns out the density that is inferred is the density expected in interstellar space and not inside the heliopause. So that's when we knew that Voyager 1 had gone interstellar. And by the way, modelers and theorists are coming to grips with the magnetometer data and figuring out that why that happened. And it's just the interaction between the heliosphere and the interstellar medium is a little more complicated than we first thought.
On August 25, 1981, as Voyager 2 was in extremely close proximity to Saturn, in its shadow and out of communications with the Earth, its scan platform became horizontally stuck. The problem wasn't discovered until communications were re-established, and after realizing that it was serious, the ground team immediately issued commands for it to elevate its instruments away from the sun to prevent damage to the sensitive optics of the various instruments on the platform. This error caused the loss of several planned observations, as most of the outbound trip was spent troubleshooting this new issue. By August 28th, the platform's azimuth actuators started moving again, though its response time was hesitant and slow. For several weeks, science activity aboard Voyager 2 is curtailed as the ground team conducts hesitant tests, concluding that it is likely the symptom of a mechanical problem within the spacecraft and not the result of any external factors. The Voyager team does not let go of their grand tour dream, and on September 23, 1981, they finally acknowledge publicly and in writing that they plan to conduct a small mid-course correction burn such that the Uranus flyby places the spacecraft on a course towards Neptune. The long chain of decision is now complete. The spacecraft simply has to survive long enough to make it there. Significant changes would have to be made in order to support Voyager 2's extended mission. The signal strength alone would be a quarter at Uranus of what it was at Saturn, and even that wasn't much at all. The solution was to array antennas together, utilizing multiple large radio dishes in simultaneous operation. Several antennas were physically enlarged. Voyager 2 had a profound effect on the current state of the Deep Space Network, inadvertently creating a state-of-the-art facility for planetary radar astronomy. Voyager-related upgrades resulted in the creation of a powerful scientific instrument on the ground in its own right. Scientists have used the radio telescopes in their current configuration to remotely study the planets without the help of probes like Voyager, leading to discoveries such as the existence of polar ice on Mercury. Voyager 2's scan platform issue is narrowed down to a problem of lubrication and worn gear mechanisms. Its movement is conserved, and the prospects for a Uranus encounter are good.
An outer space spectacular that was the stuff of dreams only a generation ago began snapping into the sharp focus of reality today. After its billion-mile journey from Earth, the Voyager spacecraft sent back pictures of man's closest look yet at the ring planet Saturn.
The spacecraft trajectory is controlled by radio tracking the spacecraft, coming up with position information from the radio data, and from the use of photographs that we take of the satellites against the star background. We convert that data into position information. Then that's combined with the radio data. That position information allows us then to compute the maneuver that we put into the spacecraft in terms of the angles that we turn through using small hydrazine rocket engines, 2/10 pound thrust engines. All of those maneuvers have been very precise. The initial trajectory is very precise. So the some 230 pounds of fuel that we had at launch is more than adequate, and there will be ample fuel left over after Saturn to continue flying the spacecraft out of the solar system.
Uranus was not discovered until 1781, when British astronomer Sir William Herschel recognized it as a solar system object. Up to that point, Uranus may have been misidentified as a star by various individuals, cultures, and civilizations across history, and likely shows up in several ancient star catalogs. Herschel, at first, believed it was a comet. What to call this new planet was something of a controversy throughout the first half of the 19th century. Herschel wanted to name it after King George III, and many English institutions, royal societies, and universities referred to it from there on as Georgium Sidis, Latin for George's star. Unsurprisingly, this name was decidedly unpopular elsewhere throughout the Western world. German astronomer Johann Bode proposed Uranus, and by 1850, the last major English institution that had held on to the original name finally gave in. Uranus is the only planet other than Saturn whose rings are observable from the Earth, though not without advanced technology. Uranus's rings were discovered the same year Voyager 2 was launched, in 1977, aboard a flying observatory operated by NASA that witnessed Uranus passing between Earth and a distant star, causing unexpected infrared fluctuations. Uranus's rings reveal another oddity about this world, the first of the two ice giants. It's on its side. All planets in the solar system rotate essentially on the same axis, conserved momentum from the original protoplanetary disk in which they formed. Venus, either as a result of tidal forces or a massive impact, spins backwards relative to the other planets, but nonetheless along the same axis of rotation. Uranus, however, is arguably stranger. The planet is tipped onto its side. Its spin, rings, and moons are tilted 98 degrees from the plane on which it orbits the Sun, the ecliptic. The current consensus is that Uranus's tilt is a result of a massive, traumatic impact early on in its formation. When our solar system formed, it is likely that hundreds of planetesimals condensed from the protoplanetary disk. What followed was a game of celestial bumper cars, as bodies competed for space, throwing, crashing into, and absorbing each other. Uranus may have suffered a glancing blow that rocked the planet over onto its side, and the fact that its moons orbit along its displaced equator tells us that they likely formed as a result of, or after this collision. Scientists now believe that all of the outer planets, after their initial formation, began moving much closer to the Sun than they are now, and it was a dramatic fight, a showdown of gravity between Jupiter and Saturn that eventually threw them back outwards. Uranus is thought to have been, at the beginning of our solar system, the outermost planet. It was passed by Neptune at some point during this era of wild orbital migration. Evidence for this is corroborated both in computer models and recorded on the surface of our moon as a temporally localized period of intense bombardment by meteoroids that were likely flung inward as these ice giants moved outward. It is possible there may even have been more planets than there are today, and these planets might still exist, ejected from the solar system outright rather than destroyed or absorbed. Like outcasts, they could wander the Milky Way, far beyond the solar system in which they formed. Could our celestial neighborhood be populated by dim, dark wanderers that once called our sun their home? Wherever and however it formed, Uranus exists now at an average distance of 19 astronomical units, fluctuating down to 18 and up to 20 due to its eccentric orbit. At a distance of 2.6 billion kilometers, Uranus takes just over 84 years to make a complete circle around the Sun. It spins once on its bizarre axis every 17 hours and 14 minutes. Each pole experiences 42 Earth years of uninterrupted sunlight, followed by an equally long period of desolate darkness. As Voyager 2 encounters Uranus in January 1986, it observes a featureless, pale blue sphere. Artificial oversaturation of images reveals that Uranus does in fact have subtle differences in brightness across its latitudes. But to Voyager, Uranus, by all accounts, looks like a dynamically dead planet. Modern imaging techniques have revealed more to Uranus than originally met the eye. Its appearance seems to be changing as its position around the Sun changes. Several clouds have been spotted. Some may have existed for decades. The planet takes on much more detail when studied in different wavelengths of light, beyond simply the visible spectrum. The key to understanding Uranus's incredibly slow, seemingly dead appearance is the lack of thermal energy within. Its internal heat is notably lower than that of the other gas planets. It hardly radiates any heat energy into space whatsoever, and temperatures within its atmosphere are as low as 49 Kelvin, or in Fahrenheit, 371.5 degrees below zero. 49 Kelvin. That's 49 degrees of Celsius above absolute zero. This may be further evidence of a massive impact in Uranus's past, which might have caused it to expel most of its primordial heat as it broke apart and reformed. Alternatively, some sort of barrier may exist that prevents heat from the core from reaching the outer layers of the planet. Like Jupiter and Saturn, the bulk of Uranus's volume is believed to be a thick layer of compressed gaseous and liquid hydrogen. Deeper down, however, it likely diverges from this model, with solid water, methane, and ammonia ice forming a type of mantle over a small, rocky core. A tiny concentration of methane in its upper atmosphere, less than 3%, is responsible for the planet's bluish color. Oddly enough, the space immediately around Uranus is hot. Gas particles in its thermosphere reaching nearly 850 Kelvin. How this heat is sustained at all is not understood. All measured variables, including solar radiation and magnetic field activity, do not even come close to accounting for this phenomenon. Speaking of magnetic fields, Uranus, unsurprisingly, has one of the strangest. Not only is it tilted nearly 60 degrees away from its axis of rotation, but it does not seem to originate from the center of the planet. It is nearly 10 times stronger in the northern hemisphere than it is in the southern hemisphere. This suggests that mechanics totally unknown in the history of human experience are at work. Perhaps these magnetic fields are generated by the convection of conductive material much closer to the surface than in the case of Earth or Jupiter. Alternatively, it may be a normal magnetic field that is somehow redirected, an effect called magnetic shielding, by some substance concentrated in its southern hemisphere. One possible material that might offer this property is diamond. Highly compressed carbon existing at extreme depths within Uranus, a compressed carbon ocean. At certain depths, this carbon may crystallize into solid, gigantic, iceberg-sized diamonds and float upwards. These proposed diamond bergs are just one speculative way we have tried to answer the nagging question of Uranus's mystifying magnetic field. The thing is, we just don't know. Voyager 2, the only spacecraft to have ever visited Uranus, is not equipped with the kind of sensitive, sophisticated, remote sensing instrumentation we would need to unlock the secrets of the ice giant's interior. It's important to keep in mind that many of these exotic claims, while scientifically valid solutions, are not observations in and of themselves. They are but one possibility among many that may explain why we've measured what we have measured. Often, the most exotic and exciting possibilities are held above the seemingly mundane. Human expectations are often difficult to temper. Because Voyager 2 is passing Uranus nearly dead-on from its rotational axis, it will be piercing through the plane on which its moons orbit, as opposed to traveling along it, as was the case with Jupiter and Saturn. The time that Voyager 2 has to make observations is exceedingly limited. It will have only 5.5 hours to make observations that for previous planets it may have had 30 or more. Voyager 2 will reach its closest approach to all of Uranus's moons essentially simultaneously. It won't be able to leisurely switch from one moon to another as it travels outward. It has to get all the data it can as fast as it can. The Voyager 2 near encounter with Uranus occurs at 10 a.m. on January 24, 1986. 4 days later, on January 28th, an unrelated incident will distract the world from this amazing, unprecedented exploration.
But the signal to launch was given and everything was apparently on course up to a minute from liftoff when the Challenger was turning on the full power of her main engines.
Challenger, go with throttle up. Roger, go with throttle up.
Explosion appeared to come from one of the solid rocket boosters which supply most of the power for the liftoff and were then to separate. Instead, the entire space vehicle disappeared in a fireball. The Challenger disintegrated and plunged downwards in spiraling debris.
The shuttle Challenger, on its 10th mission, STS-51L, breaks apart during ascent, killing its entire crew of 7. This happens the same week as Voyager 2's Uranus flyby. But what interest did exist comes screeching to a halt as the nation mourns the loss of 7 astronauts. The shuttle program, only in its 5th year of spaceflight, is put on a nearly 3-year hiatus. Uranus is so far from the Sun that light levels here are 400 times dimmer than they are around Earth. In order to get useful images, Voyager's cameras have to keep their shutters open for a longer period of time. The scan platform slews, not in one progressive fluid motion, but rather in dimensional steps. Elevation, azimuth. Elevation, azimuth. Therefore, it unfortunately cannot be used to maintain a precise pointing lock on a celestial object for a prolonged period of time. The result would be little more than a smeared image, especially knowing the precision errors already inherent in the scan platform itself. Several operational changes are made for the Uranus encounter, and one of them includes purposefully using the gyroscopes within Voyager's guidance system. The Voyager team will use the hydrazine RCS jets to aid the scan platform in target tracking by moving the bus of the spacecraft itself. This strategy would be much more costly in terms of fuel consumption, but to the Voyager team it was worth the risk. This would be humanity's only chance to get a good look at the seventh planet and its moons. Radio signals from this distance, traveling near the speed of light, take 2.5 hours to reach the Earth. Commands sent from the ground take the same amount of time to reach the spacecraft. Voyager takes a series of long exposure images of Uranus as it approaches and captures views of its Epsilon ring. Note that the spacecraft is imaging the rings head-on due to the tilt of the planet. The spacecraft also images and studies, as much as it can, what were at the time the 5 known Uranian moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Uranus's moons fall under a separate set of naming conventions than do any of the other major celestial bodies. They are not from the ancient Greek or Roman pantheon, but rather are the names of characters from playwright William Shakespeare or poet Alexander Pope, a holdover from its decidedly English origin of discovery. Uranus's moons are small and very dark. The largest, Titania, is less than half the size of our moon, with a diameter of under 800 kilometers. We know now of at least 27 natural satellites of Uranus, but these 5 remain the most important. It is likely that they all formed as a result of the massive impact that toppled Uranus over, which may explain the remarkable similarity with each other. The innermost and smallest of these moons, Miranda, is unique, both for its tiny size and chaotic topography. When you look closer, you see that significant morphing of its surface has occurred. If one measures the distance between the highest highs and the lowest lows on the surface of Miranda, this tiny moon, with a surface area slightly less than that of Saudi Arabia, has the largest cliffs and deepest canyons in the solar system. Its surface is clearly ancient, with impact craters almost everywhere. And yet, clearly, another mechanic is, or was, at play. Could Miranda have experienced tidal heating in its past, when its orbit was more eccentric than it is today? Could it be a site of active cryovolcanism? These are unresolved questions that Voyager 2 created when it observed the tiny moon in detail for the first time, and only a revisit by a dedicated exploration mission can hope to answer.
That's right, the people here in the Spaceflight Operations Facility are only one small part of the effort to keep Voyager 2 doing the job it was sent to do. We shouldn't all forget those people who are not on camera every day. Voyager, like any space project, is a team effort. And when this encounter is over late next month, Voyager will be on its way to an encounter with Neptune, of course, the 8th planet from the Sun. And these people you're seeing here will still be here, keeping an eye on their spacecraft. Voyager's Neptune encounter will bring the planetary exploration program to the end of its first major phase, that being the initial reconnaissance of the solar system. While we've learned so much from the Mariners and the Vikings and the Voyagers, we still have a lot to learn. And the people who fly these spacecraft, as well as the scientists who reap so much from the data we get, are our teachers.
Very recently, the Planetary Science and Astrobiology Decadal Survey, published as you might expect every 10 years, recommended to NASA and the Congress that the next large-scale flagship robotic mission to be developed sometime before 2032 should in fact be an orbiter designed to explore Uranus and its satellites. Not a flyby like Voyager 2, but a probe like Cassini, large, sophisticated, and able to make detailed and sensitive measurements in orbit over an extended period of time. Uranus occupies a unique position right now in the realm of planetary science. It is a high-priority exploration target, and it is likely that we will see a dedicated mission to this planet in our lifetimes, though that process has only just begun, and any results are likely decades away. These surveys, of which there are many, separated by subject and discipline, represent the general views of research institutions and academia, and they form an important mechanism of advisement for policymakers and those with the power of the purse. Their views and recommendations are exactly that. Only time will tell whether this survey's main wish is approved and funded. Uranus's orbit was calculated in 1783 by Pierre Simon, Marquis de Laplace. Certain irregularities in Uranus's orbit observed over the next several decades could not be accounted for, unless it was affected by a body of similar gravity outside its own orbit. In 1841, English astronomer and mathematician John Couch Adams set out to calculate the position of said planet, if it indeed existed. At the same time, but unknown to Adams, a French astronomer and mathematician, Urbain Le Verrier, was independently coming to exactly the same conclusion. By 1846, Le Verrier believed he had calculated the position of this unknown mystery body. Adams's work had sent the British observatories into a frenzy, and they searched all over the night sky for this purported eighth planet. Adams had sent them 6 possible solutions where this body might be found. Le Verrier, however, narrowed it down to just one. He published his own predictions in August 1846. Le Verrier was greatly disliked at the Paris Observatory, where his ambition and drive for efficiency had made him very unpopular. Frustrated and desperate, he wrote to Johann Galle, director of the Berlin Observatory, on September 18th. On receiving the letter just 5 days later, Galle searched for the new planet that very evening. He found it that night within 1 degree of the predicted position. Like Uranus, it had been previously sighted by telescopes and classified as a star. Observations made over a 4-day period absolutely established a proper motion, and thus Neptune was discovered. A German discovery from a French calculation.
A gente de férias e a casa vazia. E se ladrão roubar o portão?
Despite the fact that it had been observed by telescopes previously, no one had thought to identify Neptune as a planet. It is so faint and so far away that it cannot be seen under any other circumstances, and its existence was entirely unknown to ancient cultures and civilizations. The successful prediction and discovery of Neptune showed that Isaac Newton's gravitational laws were relevant across tremendous distances. As Voyager 2 travels further and further away from the Sun, it slowly loses its ability to navigate and align itself into attitude lock. To Voyager, our star simply gets dimmer all the time. Voyager 2 increasingly begins using its cameras to send back attitude information, specifically long exposures designed to reveal stars. Nearly 100 photos are taken of space between Saturn and Uranus for the purpose of optical navigation, and more than that are taken between Uranus and Neptune. As Voyager 2 approaches, it takes several long shots in Neptune's direction. Blemishes and Rousseau marks are removed. The natural rotation of the probe is accounted for, and the points of light are catalogued. Points that have moved between image frames more than what can be accounted for by the rotation of the probe are classified as newly discovered moons. There is so little light out here that the camera's shutters remain open for much, much longer than they otherwise would need to be around Earth. The Voyager ground team is forced to get very clever in how they manage the rotation of the probe. It was never part of Voyager's design to be able to stop all angular momentum. There are simply too many moving parts for this to be a feasible expectation. Not just the articulation of the scan platform, but even things as small as the starting and stopping of the tape recorder inside the probe can impart tiny impulses that have a collective effect over long periods of time. Software changes are made to reduce scan platform motion, enhance the gyroscope turn rate, and several others in the service of reducing spacecraft motion to accommodate increased image exposure times without incurring excessive smear. Compensating for the rotation of the probe to facilitate accurate imaging is a central focus of the Voyager ground team in the late 1980s. The light levels at Neptune are only 40% of those at Uranus. The planet as a whole, 900 times dimmer than Earth. Image smearing as a result of these incredibly long exposure times represents a serious hazard to Voyager's optical data gathering ability. They have to be able to get good photographs. It's practically the entire point of the mission. For that, they need Voyager to be as solid as a rock. Not an easy task when it's hurtling through untraveled space. Voyager 2 encounters Neptune in August of 1989, what would be its final planetary encounter. Since the probe's trajectory after Neptune would not really matter, the ground team makes a mid-course burn in 1987 to position the probe over Neptune's north pole, allowing it to fly past its largest moon, Triton. Unlike Jupiter, Saturn, or Uranus, Neptune has only one major moon. Triton contains 99.5% of all measured mass in orbit around Neptune. The 13 other recognized satellites are universally tiny, asteroid-like objects.
It's smaller than our moon. It's much colder, 390 degrees below F Fahrenheit, and so cold that the nitrogen is frozen into an icy polar cap that you see. The white polar cap in the south is nitrogen ice, but the dark streaks are geysers erupting and depositing on, and we found 2 active geysers at the time we flew by on a world that is so cold that even the nitrogen is frozen. So Voyager time and time again caused us to greatly expand what we knew about, thought we knew about planets, what we thought we knew about rings, what we thought we knew about magnetic fields, what we thought we knew about moons. It's just changed and created a legacy of discovery now for many future missions to the outer planets.
Neptune, unlike Uranus, has a fairly standard axial tilt. It experiences the same seasonal variations as a result of this tilt, though because of its incredible distance, the numbers are staggering. It takes Neptune 164.8 Earth years to circle the Sun. No human that has ever lived survived through a single Neptunian year. In fact, only just recently, in 2011, has Neptune completed one full orbit since its discovery. Neptune, like Uranus, is considered an ice giant. It does not have a solid surface, but like all the gaseous planets, instead has several layers, with a large gradient of pressure and phases of matter as you travel inward. There are multiple ways you can measure the rotation of a planet like this. For instance, you can map the shape of its magnetic field and determine how rapidly it's spinning. However, this spin is often different from that of its atmosphere, and since there is no visible surface, the rate at which that atmosphere rotates is different depending on the latitude. The equatorial regions of Neptune's atmosphere seem to make one full rotation every 18 hours, but its magnetic field rotates every 16 hours. Unlike Uranus, Neptune is radiating a significant amount of heat and energy into space, and this energy powers a vibrant and active weather system in its atmosphere. Slightly more massive than Uranus, Neptune is decidedly less hazy, with cloud formations and storms visible within. Like Uranus, Neptune's outer layers are predominantly hydrogen and helium, somewhere near an 80 to 20% ratio. Also like Uranus, a very small concentration of methane gas in the upper atmosphere gives it a bluish color. Neptune's upper atmosphere is slightly more transparent than that of Uranus. We now know from further study that Uranus boasts cloud features and banding almost identical to what we can see with visible light on Neptune. A higher concentration of upper atmosphere methane combined with a thinner icy haze layer, both a likely result from higher ambient energy on Neptune, contribute to a deeper, darker blue and more visible detail. The white clouds are likely concentrations of methane ice particles. Voyager 2 observes a couple circular storms, the largest of which comes to be known as the Great Dark Spot. Like the Great Red Spot on Jupiter, this is an anticyclone, a region of high pressure, a hole in the haze, revealing darker layers underneath. Unlike the Great Red Spot, which, while shrinking, has existed for hundreds of years, by the time Neptune was imaged again by Hubble in 1994, the Great Dark Spot had completely disappeared. Others have emerged in separate locations, suggesting that these circular storms have much shorter lifespans but routinely appear. The mechanism by which they form and dissipate is not yet fully understood. Neptune boasts the fastest winds of any planet in the solar system, even faster than the transonic belts of Saturn. Near the equator, prevailing westward jet streams moving against Neptune's eastward rotation were clocked at nearly 600 meters per second, or 1,300 miles an hour. Neptune may be 50% farther from the Sun than Uranus, and may receive only 40% of the relative solar energy, but its internal energy, radiating upward through its atmosphere, drives the fastest and most dynamic planetary winds in the solar system. Neptune has a strong effect on the shape and size of what lies beyond, the Kuiper Belt, an outer asteroid belt that lies just outside of its orbit. Neptune's gravity maintains the Kuiper Belt, which without it would likely have coalesced to form a remote, icy planet. There are several dwarf planets that call the Kuiper Belt their home. Objects like Orcus, Haumea, and Pluto. Their development, early on, was very likely retarded by the unexpected arrival of the mighty Neptune into their backyard. Neptune did not form all the way out here. It migrated fairly late into the formation of the solar system. The Kuiper Belt as it exists today is nearly 20 times larger than the inner asteroid belt, and is home to some of the weirdest and most ancient celestial bodies in the solar system. In a totally unexpected find, Neptune's magnetic field, like that of Uranus, is oriented at an extreme tilt relative to its axis of rotation, and like Uranus, does not appear to be uniformly strong around its center of mass. It is offset from the center by nearly half of Neptune's radius, even more extreme than that of Uranus. Scientists had believed that Uranus's tilted magnetosphere was a result of its sideways orientation, but now it seems that's not the case, as Neptune also shares this phenomenon. It must therefore be some internal mechanism present on both planets driving this bizarre, anomalous magnetic behavior. Voyager 2 studies Neptune's large retrograde moon, Triton. Not only does Triton orbit counter to Neptune's rotation, but its orbit is also inclined away from this axis of rotation significantly. Because of both of these factors, it is believed that Triton did not form near Neptune, but was rather captured by it. This is supported by mathematical models that suggest that Triton is slowly spiraling inwards and will eventually pass Neptune's Roche limit far into the future, breaking up into a brilliant ring system before ultimately impacting Neptune's atmosphere. Triton's surface appears to be marked by extraordinarily varied terrain, some of which has not been seen on any other body. a peculiar landscape of circular depressions, rugged ridges, impact basins, craters, smooth plains, frosty deposits, and cantaloupe terrain. How did a moon develop such interesting and dynamic topography? The answer may be cryovolcanism, the eruption and overall modification of landscapes driven by volatiles such as water, methane, or ammonia. Some 55% of Triton's surface, what Voyager 2 was able to directly image at least, was covered in frozen nitrogen. In this regard, Triton is very similar to Pluto. However, Triton seems to lack the dark, reddish hydrocarbon sludge that we see on Pluto. It should be noted, however, that one whole side of this intriguing moon remains unobserved. Equally important, telescope observations of Triton in the 1960s seemed to indicate it was reflecting a much larger amount of red light than it was when Voyager 2 ultimately flew past it in 1989. The appearance of the moon may have altered considerably in the intervening time due to cryovolcanism. It may even look very different today than it does in these 30-year-old photographs. As Voyager 2 images Neptune with the sun behind it, like on each of its planetary encounters before, it discovers new and unseen rings. These images are the result of 591 seconds of exposure, a nearly unheard of amount by earthly standards. Nearly 10 straight minutes of uninterrupted light gathering. As Voyager 2 pulls away from Neptune in 1989, its planetary phase comes to a close. Like its sister, Voyager 1, it begins what is called the interstellar phase of its mission. For the remainder of its life, it will make observations of our star as it travels ever further, mapping and measuring the sun's magnetic field, much as it did those of the planets. Each Voyager spacecraft carries on its side a gold-plated, 12-inch, two-sided stereo phonograph record, enclosed within a record case alongside a small stylus designed to read and play back the audio information embedded in each record. These records, known as the Golden Records, can trace their roots back to Pioneer 10 and 11. An English journalist named Eric Burgess believed that the two Pioneer probes, which themselves were bound to interstellar travel, should carry a message for extraterrestrial intelligences. He took this idea to a well-known and very vocal NASA advisor, a professor at Cornell University and director of its Laboratory for Planetary Studies, Dr. Carl Sagan. In the 1970s, Carl Sagan would rise to national prominence as a science communicator and advocate for the search for extraterrestrial life. Working in his advisory role for NASA, he garnered significant influence over American robotic space exploration. Sagan was so taken with the idea that the Pioneer probes should carry a message from humanity that he was able to convince NASA to incorporate a small, lightweight plaque onto the two vehicles. Sagan would expand on this idea considerably for Voyager. Borrowing several symbols from the Pioneer plaques, the Voyager record covers are essentially a blueprint, a list of instructions that, if followed, would allow an alien intelligence to unlock the contents of the records themselves. Carl Sagan was never considered a member of the Voyager team, and the Golden Records did not contribute to their mission. His influence over NASA's operational affairs is to some controversial. Few, if any, actually expect Voyager's Golden Records to ever be found and read. The probes are, celestially speaking, tiny and dark. They emit no major radiation and are many degrees of magnitude smaller than even a small asteroid. What these records instead represent is a level-headed attempt to develop a system of communication that is free of any cultural or circumstantial influences. The challenge facing Sagan and the Golden Record team was, how do you communicate complex ideas without any cultural or biological frame of reference whatsoever. What concept would an alien intelligence have of time? They wouldn't know what a second was, a minute, an hour. Instead, the Golden Record team would have to rely on universal constants, numbers and figures derived solely from the cosmos. The most important symbol on the Golden Record's cover can be found on the bottom right. 2 hydrogen atoms, each just 1 proton and 1 electron. The hydrogen atom on the right has its electron facing outwards, and the other depiction shows its facing inwards. In a neutral hydrogen atom, at its lowest and most basic energy state, the proton in its nucleus and the lone electron in its valence shell spin in opposite directions. That is to say, their spin is anti-parallel. However, if a small amount of energy is introduced into this system, say from a collision with another atom or from radiation, the electron can become excited and enter a slightly higher energy state whereby its spin aligns with that of the proton at the nucleus. In this higher, parallel energy state, the electron and the proton are now spinning in the same direction. Eventually, that energy has to be dissipated. When that happens is seemingly random, subject to the forces of quantum mechanics of which we understand very little. But sometime in the next 10 million years, that electron will suddenly and spontaneously drop back down to the ground state, and a small amount of energy will leave the atom in the form of radiation. A radio wave, randomly emitted from excited hydrogen atoms, pervades the universe. It is found practically everywhere. It is incumbent on no one planet or star or phenomenon. It is truly omnipresent. The line you see that divides these 2 hydrogen atoms measures 23 centimeters across on the record cover, and this wavelength, in hertz, represents the fundamental unit of time in which all the other symbols here are represented in binary code. Others on YouTube have explained the records far better than I can, and I encourage you to watch those videos, links below. The information embedded within the cover communicates a step-by-step process towards playing and understanding the Golden Record. The first side of the stereo record is fairly straightforward. It contains music, greetings, and the sounds of animals and nature. The second side, however, is much more interesting. It is a series of varying tones, each separated by an audible beep. These tones are images encoded in audio signals. The pitch in tones corresponds to brightness values, and the timing corresponds to location. These images are meant to be displayed on a classic standard definition CRT television, 512 lines of resolution. Each line 8.3 milliseconds. Each image 4.2 seconds worth of audio. Because the record is in stereo, the images are played back 2 at a time, with 2 streams of audio relaying separate information. People like Ron Berry, using modern digital technology, have followed the record cover's instructions and have unlocked the content hidden within Side B, showing that the method of encoding remains relevant even today. Even if an alien intelligence found Voyager, which nearly every measurable reason suggests is impossible, one can't know whether Sagan and his team would ultimately have been successful in their attempt at communication. What it does represent, however, is a template for future generations of humans to build on. It was the approach developed, not the record flown, that ultimately served the experiment's purpose.
The first successful interplanetary mission of the human species was the Mariner 2 NASA spacecraft, which flew by Venus in 1962. The Voyager 2 flyby of Neptune occurred last year, that is 1989. In those 27 years, the human species has flown close by or orbited or landed on every one of the planets. We have completed the preliminary reconnaissance of the solar system. There's only one time in history when this happens, when for the first time humans send their artifacts and themselves off the Earth and explore their local neighborhood in space. It's our great privilege to be alive at that first moment. Think of the number of objects that we now know are in the solar system that we didn't even know existed then. Then think of how many were mere points of light, where we had no idea what the surface features or any details were. And then think of how wrong we were in our guesses about so many of the objects that we did know, thought we knew something about. Voyager and Viking have wholly changed our knowledge of the solar system. Not, of course, the celestial mechanics of the planets. There are a few verities, but everything else is kind of prehistoric. The history of real knowledge of the solar system begins in that 1975 to 1989 period. Now, of all those worlds, including the 56 moons that the two Voyagers explored that Dr. Stone mentioned, we have no indication of life. There are the stirrings and intimations, if you like, where it's very clear that complex organic molecules are being formed, but there is no evidence, not a smidgen of evidence, suggesting life anywhere else. And for me, that underscores the rarity and preciousness of the Earth and the life upon it.
Also thanks to Carl Sagan, in February of 1990, Voyager 1, at a distance of 40 AU, turned its cameras inward and photographed a pale blue dot of light. Its last look at the Earth before its imaging system was powered down.
To me, the mission has personal relevance, not because I was ever involved with it, but because as a child, the encounters with the various planets, actually the two final planets, Uranus and Neptune, helped to define my childhood and also helped to define my own understanding of our place in the solar system. I was too young to enjoy the flybys of Jupiter and of Saturn, but Uranus and Neptune I remember quite clearly as a kid, seeing the images on the news in the evening news and just really being impressed by what we were doing out there in the solar system, that I could feel that I was one of the first to see these planets in such great resolution. And I'm sure that several others of you who, like myself, perhaps were born in the 70s might feel the same way.
Voyager 1 was actually launched second, but it is traveling the fastest. It's the furthest spacecraft from us. It travels at 38,000 miles per hour approximately. Nothing's going to catch up to it. And Voyager 2 is traveling a little bit slower, 34,000 miles per hour approximately, but that's still 40 times the speed of sound here on Earth. The Voyagers are healthy and as healthy as senior citizens can be. That's the way I like to think of them. They're twin spacecraft, identical, and think of them as twin sisters, senior citizen sisters. So each has had different ailments over the years.
The two Voyager spacecraft are still alive right now. Though over the years, as their nuclear fuel source has decayed and their power output has diminished, the instruments and heaters on board have been shut down one by one. They are operating now as a fraction of their former selves, but continue to make observations of charged particles in the space around them. Both probes finally traversed the boundary between the solar wind and the interstellar wind, decades after it was predicted they would. In space for 44 years and counting, Voyager 1, the furthest man-made object from Earth, is 156.5 astronomical units from the Sun at the time of this video's production. 156.5 times the distance between Earth and the Sun, 21.5 light hours. It is expected that the probes will continue to operate until 200 AU in the early 2030s. Both Voyager probes have surpassed all expectations. Their contributions have single-handedly shaped our knowledge of the solar system and the universe. Their data, both old and new, lives on in the contributions and interpretations of new generations of scientists and artists. These two robots represent the best of us, our highest ideals, our highest ambitions. Their story ongoing, the history preserved.